Okay. Good morning, everyone. I believe that the sound is clear. Okay. All right, so today we are looking at the first part of our chapter 16. And in the chapter 16, we'll be looking at superposition and standing wave. We're looking at superposition and standing waves. You have to answer the question of this Aboriginal tribe person that is blowing this musical instrument and how he's able to make different notes using this long device. We'll be able to answer this question at the end of this chapter. Okay. So, as usual, the chapter will be taking 3 sections. And in the first one, which is the one we'll handle today, we'll be looking at the superposition, where we'll be describing how that 2 waves can add up or cancel out. And by that, we mean the constructive and destructive interference of wave. We'll be looking at that as we discuss superposition. And by next class, we should look into the details of standing wave, although we'll be introducing it in this first lecture as well. But by next class, we should be able to look into more details on how standing waves are created and how they also are interpreted with a sound wave. And we'll also be looking at speech and hearing at the later end of the chapter. The goal is actually to use the idea of superposition to understand the phenomena of interference and standing waves. Okay, it is this phenomena that also forms the way we produce sound using our vocal tract, and also how we mix sound using different mix of waves. Okay, so that is simply the goal. At the end of the class, we should be, at the end of the discourse of this chapter, we should be able to understand the phenomena of interference and standing waves. Okay, so we'll begin today's discussion by looking at the principle of superposition. Now, when we say superposition and we emphasize on the principle, it simply means that we actually want to see the basics of operation or the basis to understanding superposition. Let's look at the figure before us, the figure A and B. You notice that the figure A describes the motion of a baseball. Now, 2 baseballs can actually move in opposite or adjacent direction. When they collide, this is what happens. They hit off each other to different directions. But this does not happen this way when we start describing sound wave. So the figure B describes the motion of sound wave. We see that sound wave can actually pass through each other. Unlike the baseball, when they hit each other, they bounce off. But for the sound wave, when they meet, they pass through each other as if nothing happened. And you see the 2 loudspeakers producing different sound, and each Bill and Allen can hear the sound produced on these 2 speakers. The sound here travels to this direction, passes through the other one, traveling in the other direction, opposite direction, and they pass through each other as if nothing happened. Okay, so this is what we actually refer to as the principle of superposition. Sound or waves can actually pass through each other, unlike other objects. Now, if you look at the figure here, the picture here, this later diagram, this actually explains what we mean by two waves on stretching, passing through each other. All right. So whenever you think of the principle of superposition, think of it as sound or as waves having the ability to pass through each other as if nothing happened. We see the wave 1 and wave 2. Wave 2 here, wave 1 here, traveling in opposite direction, and they approach each other. Here, they meet and overlap. So as they overlap, you notice that the amplitude of each of them increased because they combined. So they pass through each other and continued their journey as if nothing happened. So this process of wave being able to pass through each other and continue on their track as if nothing happened is what we call superposition. And that is the principle that governs superposition. We'll also see how we define that. So the principle of superposition says when two or more waves are simultaneously present at a single point in space, the displacement of the medium at that point is the sum of the displacement due to each individual wave. Okay, so that's the principle, because we know that they pass through each other as if nothing happened. So when they are present at the same time in the space, the displacement you see on the medium is actually the sum of the individual displacement of that wave. Now, to further buttress what we mean, we see this figure here showing us the superposition of two waves on a string and how that they pass each other. So regardless of the shape of the wave, as long as it is two waves meeting each other, they superimpose, that is, they add up to give you a kind of motion on the medium through which they are propagated. And that is the general principle that governs wave. So we see this wave and this wave traveling at the same speed. So they approach each other as shown here. At the time t equals to 1 second, they meet at this junction and they combine here at time t2. The combination, look at the combination of these two waves, the rectangle plus the triangle, giving you this shape. And they begin to propagate or pass each other. So at the point of superposition, we see the net displacement is the point-by-point summation of the individual waves. So the general shape you see here is the summation of these two rectangle and triangle wave. So they begin to separate out at this point C3. The triangle continues its journey and the rectangle continuing its journey. And they separate out, both waves emerge unchanged in the end. They separate out. After combining, they emerge out unchanged and continue. So this is what we mean by wave traveling through each other. And this is the general principle of superposition. Now let's look at another interesting thing that happens during superposition. We can either have what we call a constructive or destructive interference. The superposition of two waves is often called interference, right? So it means the addition of two waves is what we call interference. So we have constructive addition, and then we'll have destructive addition as well. The destructive addition cancels out, while the constructive addition add up. Okay, so we see the example also of two waves in motion here. The displacement of the two waves as shown in this figure are both positive. So the total displacement of the medium is the shape we'll see where they overlap and form a larger amplitude such that we describe it as constructive interference. Okay, so the same principle holds, two of them. At this point, the displacement is zero, they cancel totally. And when this happens, we call it destructive interference. But when they add up to form a larger amplitude, then we can say it is constructive. And they continued also, both emerge unchanged, the same description we had before. So the figure emphasized at the point, this point here, where t was 1.5 seconds, that a destructive interference occurred there. Okay. This is a typical example of constructive interference, and this is a typical example of destructive interference. Destructive interference is when the displacement of the medium where the wave overlap is less than its, in terms of amplitude is less, or we can say it is less than it would due to either the waves separately. So the wave itself, when they're individually, when they overlap and it's less than what each individual displacement would be, then we can say it is destructive interference. So the principle of superposition still holds, but now the displacement is actually in the opposite direction, so it reduces or totally cancel out. Okay, we will also see that in our example. So let's look at this class activity. We have these two waves traveling in opposite direction at the same speed. The two pulses on the string approach each other at the speed 1 meter per second. What is the shape at the time t6? Okay, so if you look at these two, what would this shape be at time t6? At time, yeah, this is distance times 0. If it moves to 6, and this moves as well at the same time, what would be the shape? Is it A, B, or C? Okay. Now, the answer is C. If you look at the two waves, at the time T6, when you go to T6, the shape of the two superimpose. Okay, and when they superimpose perfectly, the superposition is the point-by-point addition. Okay, each of them, as you can see, the displacement add up, and the two individual waves form this shape on the medium. That is why we choose C as our answer. Okay, so let's proceed to introducing a standing wave. In our last class, we saw traveling wave. We discussed the whole of chapter 15. We used it to talk about traveling waves. We emphasized waves that carry energy from one point to another, point A to B. But here we're meeting another kind of wave we call the standing wave. Okay, how is it different from the traveling wave? It is actually different because, like the name depicts, the other one is traveling and this one is sitting on a position. Okay, so let's imagine you having like a rubber band in your hand and you stretch it and you pull, or your guitar string, you, you, you make a sound on the guitar, you see it vibrate, but it's vibrating on its position, it's actually not going anywhere. So you see that because the two ends are bound or fixed, you see the vibration at the standing position. This kind of wave produced is what we refer to as standing wave. So the individual points on the string oscillate up and down, but the wave itself does not travel anywhere, it doesn't move. It is standing, and so we refer to it as standing wave. We call it standing wave because the crest and the trough stand in place as it oscillates. The crest and the trough, they are standing at the position as the oscillation, up and down oscillation take place. Okay, so standing wave is simply the wave that the crest and the trough stay or stand in place as it oscillates. So let's see superposition created by standing wave. So the superposition creates a standing wave. Let's see how that happens. So suppose we have a string on which two sinusoidal waves of equal wavelength and amplitude, note the word equal wavelength and amplitude, travels in opposite direction as seen in this figure A here. We see this wave and this one, they have equal wavelength and amplitude, but they are traveling at opposite direction. Remember, we want to see how that superposition creates a standing wave. And you know what a standing wave is? The wave that is not moving or going anywhere or bound at two ends. Okay. So if we imagine or picture these two waves having the same magnitude, the same wavelength, but traveling in opposite direction, we have already said the principle of superposition is that waves can actually add up, pass through each other, and emerge unchanged, right? So we suppose that that will happen with these two waves as they approach each other. So let's see the analysis of what happens to these two waves from our figure B. Our figure B is also extended to the next slide. So we begin with the field that we have. We have the red line here to represent the wave that is traveling to the right, this one. And then we use the orange color line to represent the one going to the left. We will use also the blue line to represent the superposition of the two waves. Okay, so that's the three colors that we have here. So at time t0, we see that the orange and the orange and the red, look at it, they are coming in to add up with one another, and we have the superposed sinusoidal graph to be of this shape. Okay, so we see the two trough adding up to be higher than the usual red and gray sides. So that's why you see the blue always having a bigger amplitude. Okay, so at time t 1/8t, at this time the wave exert overlap and superposition gets to maximum. You can see the two, they have overlapped perfectly as if it's one line. You can see it. Then the emergence wave, which is the blue line, the result of the overlap or superimposition, is this blue line here. Okay, so the same thing keeps happening as the overlap. We see the emergence wave graph also appearing. But when it got to time t 3/8, we see something interesting happened. All this while, the overlap has been forming a constructive interference. Overlap of two waves is what we call interference. So it has been forming constructive interference. We mean it is giving us a sinusoidal shape as the result of the two summing up together. But when we look at what happens at this time, we can see that at this time, the crest of the red meets with the trough of the orange. The crest meeting with the trough. And what is happening is that they cancel out. So when this happens, they actually, in the medium, it's as if nothing is happening. It's as if there's stillness. And then a wave will emerge again. So they cancel out to give a straight line or stillness. Okay. So when that happens, that definitely happens somewhere at time t 3/8 period. Okay. So when that happens, there was stillness and they continued to travel through each other and they emerged again, gave us the constructive interference, the position where we also had or have the maximum amplitude where they perfectly combined. Okay. And then we have also where the overlap cancel out again. So the resultant superposition graph is what we see on this side. So this is what's canceled out and they continued again to give us constructive interference. So we'll have a total of 9 different measured graph, 3 constructive, 1 destructive, 3 again constructive, 1 destructive, and so on. Okay, so that's how superposition creates the standing wave. We see a time comes where the two of them combine perfectly to become one wave, and then they cancel out totally as well. Okay, so let's look at the description of a standing wave. How really do we describe the sinusoidal shape from a standing wave? We use the two words nodes and antinodes to describe or define our wave. So let's see the figure here that is showing us like a, in the snapshots at different times from the two waves we saw earlier. If we combine or superimpose this particular resultant superpositioned wave as one, we can see the different shapes and then the one that canceled out, one combining trough, crest and trough, and the ones that canceled out. So, but if you look closely at the diagram, you see the points here is what we call the nodes, and the crest, trough, is what we call the antinodes. We notice that the nodes and antinodes are spaced with half lambda. They're spaced by half lambda. And this means that the wavelength of a standing wave is twice the distance between successive nodes. So this is how we have the wavelength. It's actually twice the distance between successive nodes. 1, 2. Okay, so that's when we'll have one wavelength. We'll have 2 successive nodes to give us one wavelength. And we want to note that what actually happened that we call the nodes is actually the point where the displacement of the 2 traveling waves are equal in magnitude, but they are opposite in direction, so they canceled out. All right, when that happens, the superimposed outcome formed a destructive interference. So at that point, the displacement is 0. So when we see the node at constant interval, like the spacing of lambda over 2, we keep seeing nodes. It means that destructive interference is happening at that point. Okay, so destructive interference occurs at the point where we have the nodes, and constructive interference occurs at the point where we have the antinodes. Okay, so the antinodes sum up the displacement to give you a larger one. All right. So if you look at same description of standing wave, we have emphasized the nodes, the antinodes, and we have also emphasized that the nodes are points of destructive interference, while the antinodes are points of constructive interference. And we want to look at another important point, which is the intensity of the standing wave. So I've seen different characteristics of standing wave. We've seen the nodes, we've seen the antinodes. We have emphasized that the wavelength is twice the distance of two antinodes. Now we want to look at the intensity. If you look at this diagram and then the individual sinusoidal wave, we see that the intensity is maximum at the antinodes. Well, at the nodes, the intensity is 0. Look at it. But it comes to maximum here at the antinodes, which is the crest. But the nodes, we're looking at one side, the node is actually 0. So the key idea is that the intensity is maximum at the point of constructive interference and 0 at the point of destructive interference. The point of constructive interference is the nodes for standing wave, and the point of destructive interference is the point of constructive interference is the antinodes, while the point of destructive interference is the nodes. This is destructive and this is constructive. All right. Okay, so let's see one example before we call it a day. Two children hold an elastic cord at each end. Each child shakes an end of the cord 2 times per second, sending wave of 3.0 meter per second towards the middle, where the two waves combine to create a standing wave. What is the distance between the adjacent nodes? Okay. So from the information we have, the interval for spacing of nodes in standing wave is lambda over 2. And then we'll have established relationship in chapter 15 that we use to solve problems. That is this equation showing the relationship between wavelength, frequency, and speed. So we'll adapt that formula, made wavelength the subject of formula here. The speed is given to us, the frequency was given as well. We use that to look for the wavelength. But the information about wavelength that we know for standing wave is that wavelength is actually, the nodes are actually at distance lambda over 2. So see, this is our lambda, we divided by 2 to get the distance of the adjacent nodes as the question has requested. Okay, we see that it's actually a straightforward problem. So let's see this class activity and then we'll call it a day for today. A standing wave is set up on a string. You know how that is produced by pulling the string. A series of snapshots of the wave are superimposed to produce the diagram you see here. Just like you saw how we superimposed the 9 different snapshots to give us the diagram we have there. That is what we do whenever we have problems given to us we superimpose to get understanding of the question asked and how to navigate to our answers. So the question is, what is the wavelength? I've superimposed several snapshots to give us the image we have now. What is the wavelength? Then we will set up on the string. So we'll have the total distance for these 3 antinodes to be 3 meters. What is the wavelength? So this is the answer. The answer is D. Wavelength is 2 meters. And how did we arrive at that? We know that there is a node at each end, right? And we also have 2 nodes in the middle. So the distance between nodes, since we have 5, is 1 meter. All right. So the distance between successive nodes is therefore 1/2, which is half. So substituting that, we have the wavelength to be 2. If the distance is 1, the next will be 2. So have these quick questions for you to practice with, and we'll see in our next class. If you have any question, comment, feel free to send it to me and we'll discuss it as required. All right. Please go through these questions and practice them. Thank you so much. Have a great day. Bye-bye.